Well, welcome everybody to this new section of the Seminar course. Today we are very pleased to have with us Professor Ortigosa, who is going to talk us about accelerating the design of active materials through multifunctional topology optimization. But before that, Professor Javier Bonet is going to introduce our speaker today.
Okay, thank you very much, Ignacy. I'm assuming the camera that is okay. So thank you very much, Ignacy, and it's a real pleasure to be able to welcome to Sydney to Rogelio Ortigosa. By the way, for those of you who don't know me yet, I'm Javier Bonet. I'm the new director of Sydney. I've been here for 2 months, coming to 2 months at the moment. But really, it's a pleasure to be able to welcome Rogelio to Sydney to deliver this seminar. I'm particularly pleased that Rogelio has made the effort to come all the way from Cartagena. Nowadays, we can do these things in a hybrid format, and many of you are attending this seminar via Google Meet. But it's great to have Rogelio here. I've known Rogelio for quite a while. Rogelio came to Swansea a number of years back to do a PhD with my colleague Antonio Hill and myself, and probably has been one of the strongest PhD candidates and students that we had in recent times. So much so, and I remember when we were starting to work with Rogelio, and Rogelio was starting his PhD and developing early thinking as to what the thesis was going to be, we realized that Rogelio's ability to develop algebra and equations was so overwhelming that the reality is that we practically had to invent a new notation so that we could keep up with the algebraic developments of Rogelio. And in some respects, that was the main motivation for the development of the tensor cross product. So we could, in some manner or form, keep up with the way that Rogelio was developing all the equations for very complex models for large strain materials. So in some respects, that led to new areas of research, but that was thanks to the capacity of Rogelio to deal with very, very complex algebra. Rogelio finished his PhD in Swansea, a brilliant PhD that I think received many awards in the UK and in Europe. We did our best to retain him in Swansea. He did obtain actually a very prestigious fellowship, a Sir Cymru. Sir Cymru means stars in Wales. Sir in Welsh means star. Cymru is the Welsh name for Wales. So Rogelio obtained a Sir Cymru fellowship to stay in Swansea for a number of years. But I think the pull to come back to Spain, and in particular to come back to Cartagena, was too strong, and eventually left Swansea to think for a Juan de la Cierva fellowship also in Spain. I don't quite know how long ago that happened, but 4 years ago. Okay, so you've been in Cartagena for 4 years, and I'm delighted to meet with you again. We've met a couple of times in a number of places around the world, in either conferences or courses, but it's great to have you here in person, and I very much hope that we'll be able to continue doing things together into the future. I'm sure that the topics that you're going to be talking about today are going to be tremendously interesting. I can see that you have very generously put my name at the end of that list of co-authors. I'm sure that's more out of generosity than anything else, but I really look forward to hearing what you have to say. Thank you very much, and over to you, Rogelio.
Okay, thank you very much to everybody. It is a real pleasure to be here in front of this really expert audience, and it's a real pleasure to have been introduced by my former second PhD supervisor, who I have to disagree with him because there is a lot of merit coming from his side on the work that I'm going to be presenting today. It's just the only time that I have disagreed with Javier. Okay, so the work that I'm going to be presenting today is actually a good summary of what I did during my PhD and postdoc at Swansea University, and what I've been doing recently at Cartagena. So there are a number of contributors to my work coming from Swansea, and as Javier mentioned before, Antonio Gil, Javier Bonet, and also Rampolla. But in Cartagena, I've been lucky enough to meet Dr. Jesus Martinez Frutos. Some of you already may know him. And with him, we have exploited the background that I acquired at Swansea and explored it in the context of inverse problems, as you will see during my presentation. So my presentation is a bit ambitious in terms of length, but I'll try to do my best. And it's going to be split into 3 parts. The first part, it is a must to start with the application. I need to motivate the work that I'm going to be developing or presenting afterwards. Then the second part is going to deal with elements of nonlinear continuum electromechanics, which is basically the common denominator or the common factor, the common feature of all the developments within my presentation. And then later on in part 3, I will try to apply the techniques that I mentioned before regarding inverse problems into that field of nonlinear continuum electromechanics. So the application. I'm interested in smart materials, smart or multifunctional materials. And there is a number of materials that respond to that category on this circle. For instance, you can see this material, electro-responsive material here. What does it mean? It means that when you apply an electric field, this material can change its shape, right? You also have pressure-responsive materials. This material has inner channels. Throughout the inner channels, you inject a liquid, and because of the pressure, this material is going to exert or is going to exhibit some changes in shape, and so on and so forth. You also have magnetomaterials or magneto-responsive materials, on which the application of a magnetic field is going to deliver that change in shape. Okay, but the common factor, the common feature on all these materials is their flexibility. Okay, that's the key feature, flexibility. Why? Because that makes them ideal candidates for the field of interest of my presentation, which is soft robotics. They can be applied, they have a tremendous potential in the field of soft robotics, shape morphing applications, and so on. Okay? Specifically, I'm going to focus in my presentation, if I have time, on 2 types of materials. The first type of material responds to the category of electroactive material, and it's a specific type called dielectric elastomer. The dielectric elastomer is essentially a very flexible polymer, which is incompressible, but it is a capacitor, right? So you can think of a capacitor. You put an electrode on top and bottom. This is actually the first image the first picture that you are going to find if you Google dielectric elastomer. You're going to see that. You put an electrode on top and bottom. You generate an electric field, an electric potential gradient across the thickness. Coulomb forces are going to generate an attraction between the electrodes, and as the material is flexible, there is going to be a reduction of thickness. And as you can imagine what's going to happen in the opposite, in the perpendicular directions. There's going to be an area expansion due to the incompressibility. Okay? But that's not the interesting feature of this material. The interesting feature is that those electrically induced deformations can be massive, as you can see here. This is a dielectric elastomer prior to the application of an electric field, and you can see what happens when you apply the electric field. It's a massive electrically induced deformations. And that makes them, like I said before, ideal candidates for their use as soft robotics. For instance, you can see here an application of a soft gripper. The gripper is actuated electrically, and then you can imagine what's going to do. It's going to grasp an object. Okay? This is one of the materials that I'm going to be mainly focusing during my presentation, and there is one that I'm going to briefly mention in one application, but which is very interesting. It is very interesting because the working principle is very different. It's actuated magnetically. So it's a composite which comprises elastomeric, a very flexible elastomeric matrix, and it's going to contain inclusions, rigid inclusions. All right, and then the way we are going to actuate the materials is in 2 stages. In the first stage, we are going to apply a magnetic field within these coils, okay? and we are going to saturate the material. There is going to be a remnant magnetic induction. If you are not familiar with the field of magnetics, you can think of it like a plastic deformation, all right? That remnant magnetization that I'm denoting like B0R can change or can vary spatially. You can have different patches of remnant magnetization. Why? Because at the second stage, we are going to place again the material within the coils, and due to the interaction between this applied magnetic field and the remnant magnetization, this magnetic field is going. What? I don't know what happened. Can you help me here? This magnetic field BA is going to try to align the remnant magnetization, and as a result of that, you can have very cool shape-morphing configurations. Okay, that is the objective. So two types of materials, and then if we understand then the working principles of those materials, and we know the partial differential equations that govern their behavior, what we can do is to try to apply, if we know inverse techniques, we can apply them to design these materials, okay? But before designing them, I need to go through a not so exciting topic, which is basically covering the basis behind nonlinear continuum electromechanics, which is what I'm going to be trying to do in the next part of the presentation. So nonlinear continuum mechanics, everybody starts with the potato. We don't like the potato, we prefer this fancy picture here. So nonlinear continuum mechanics, we always have the reference configuration or material configuration. In this case, the deformed configuration is going to be achieved through electric field. I'm going to be focusing on electromechanics here. Nonlinear electromechanics. There is going to be a mapping phi that you can see there, which is going to be linking material particles, capital X, from the material configuration, to the spatial configuration, that's small x. We assume that the mapping is bijective, etc., etc., etc. Associated with that mapping, we typically define the deformation gradient tensor like this. That nabla 0 is actually the material gradient or derivatives with respect to capital X, okay? In addition to define F, we can define the Jacobian, which is, or the determinant of F, and its cofactor. Why are those important kinematic entities? Well, because these kinematic entities are responsible of the transformations of infinitesimal elements of line, area, and volume from material to spatial configurations, all right? But they are also going to be important not just from a physical standpoint, but for the definition of constitutive models, which is what I'm going to be presenting later. Like Javier said before, I needed to have a more amenable algebraic expression, especially for the cofactor. And then, thanks to Javier, he came up with this tensor cross product operation, which essentially we are writing exactly the same. This is typically how you would express the cofactor, but the cofactor can also be expressed in terms of this tensor cross operation, all right? And then the Jacobian can be expressed like this. Why do I prefer this? Because typically in nonlinear continuum mechanics, you are going to compute first and second directional derivatives of these kinematic entities, and this makes my life easier. What notation you prefer, that doesn't matter. In my case, I prefer this because it's going to make my life easier, much easier. Okay, but now I need to present the governing equations in nonlinear electromechanics. Okay, I'm going to discard magnetic effects and time-dependent effects, all right? In which case, the Maxwell equations are going to reduce to these two. This is the Ampere law, and this is the Gauss law. In the Ampere law, basically, we are asking that the rotational of the Lagrangian or material electric field is 0, it has to be 0. And that can be satisfied by introducing a scalar potential phi, which is this guy here, which is what we usually call the voltage or the scalar potential, right? And in the second equation, this is the Gauss law, where you have this vector field D0, which is called the electric displacement field. And then typically there is a volume charge, electric charge, which is 0, that one. And essentially we have Dirichlet and Neumann boundary conditions. Dirichlet over the electric potential. The mechanics equations are actually identical. So this equation is nothing else than the compatibility equation, which is very similar to the Ampere law. Basically, that the rotational of the deformation gradient tensor is 0, which can be satisfied if you define F as a material gradient of your mapping phi. Okay, it's essentially the same. And then we have the equivalent to the Gauss law, which would be the conservation of linear momentum. This P is the first pure Kirchhoff stress tensor, and this B0 is volumetric force. And then again, Dielectric and normal boundary conditions. So we have like 4 entities here, 4 fields, first pure Kirchhoff, F, B0, E0, and they are going to be interrelated through a constitutive law. Okay, typically we define, well, a strain energy function, which in my case I call it internal energy, from which I'm going to derive those relationships. And as you can see, there is a word conjugacy between P and F and E0 and B0. This is the way I'm going to define my constitutive law. But the key thing here is actually how to define that constitutive law. Can we define any constitutive law? Is it possible to define any constitutive law? The reason, the answer, is no. At least there should be some mathematical constraints, physical as well, like objectivity and so on, but there are some mathematical constraints that need to be satisfied. A reasonable constraint is that the constitutive law needs to be rank 1 convex. This is actually the expression for rank 1 convexity, where this guy here is nothing else than the Hessian of this. So basically, a 2 by 2 sort of tensor with the second derivatives of this energy. I'm not asking E to be convex in F and D0. I'm asking it to be rank 1 convex. You can see here a tensor which is rank 1 convex, matrix, and this is a vector. The question is how to define E being rank 1 convex. Well, we use a sufficient condition called polyconvexity, which is very well established in the field of mechanics. In the field of mechanics, Sir John Ball postulated that the energy is going to be polyconvex if it can be written as a convex combination of F, H, and J. And what we did in my PhD was to extend this work to the field of electromechanics. Basically, in electromechanics, you need to incorporate the electric displacement field in the material configuration, and also this field, which is not the push forward of this one, right? It's going to be a coupled field which incorporates the product of F and D0. A very simple model that summarizes that is actually the one that you see here. So this would be, first part is purely mechanical, it's a Mooney-Rivlin material, which would be convex in F, H, and J, provided that F is a convex function. And then you have a convex function of D0 and a convex function of D. However, forget about this electromechanical term. If you want to understand polyconvexity, what it means, just focus on this one. This is clearly convex in these 3 entities. But this one, if you see it as a function of F and J as well, this would not be convex with respect to F. And this is good, because if it was convex with respect to F, we would be precluding buckling. And we want the model to incorporate buckling, especially when buckling is going to be induced now by this electromechanical argument. Okay, buckling is not going to be only included, induced by loading, mechanical loading. It's going to be induced by electricity, by electric field. Okay. Some researchers, however, prefer to work with the Helmholtz energy. And that Helmholtz energy is a dual energy to the internal energy that I presented before. And that can be obtained through a Legendre transformation with respect to E. Okay? For instance, in the case of this very simple model, I have a Mooney-Rivlin material, and then this one is a typical case that you would see that we denote like ideal dielectric elastomer. This is a very, very simple model, all right? This model is convex in F, H, and J, and this is convex in J and D. When you analyze the convexity of these terms, you can analyze them separately because there is nothing coupled, but in this one, J and D are coupled. So you need to look at the Hessian with D and J. And this is convex, okay? Well, for this model, it is very simple to get the analytical expression of the associated of the dual Helmholtz energy, all right? For more complex models in the internal energy, especially non-linear with respect to D0, this analytical or explicit expression is not going to be available. And you need to resort to a Newton-Raphson type of scheme, okay, in order to get the Helmholtz. Okay. That is the theory, but now the finite element implementation of this. The finite element implementation of this, we need a variational principle. And that variational principle is essentially the one that you see here. It's postulated in terms of the Helmholtz, which is defined as the dual energy of the internal energy that they defined before. And then you have these external terms and so on. We compute directional derivatives, the stationary conditions of this variational principle, and you get essentially the weak forms of the PDEs that I presented before. All right? As you can see, it is a two-field formulation where the unknowns are going to be displacement and electric potential. So you can imagine your stiffness matrix after when you discretize this, like having like 4 blocks: mechanics, mechanics and phi, and x, phi. All right? Cool. So polyconvexity brings benefits not only from the constitutive standpoint. I didn't justify before the selection of or the satisfaction of the Legend-Hadamard condition. I should have said it before. Why do we want our energy to satisfy the Legend-Hadamard condition? From a mathematical point of view, it's because the PDEs, the system of PDEs, is going to be well posed, which means that there is continuous dependence with respect to the data. From a physical point of view, it means that if you extend it to the dynamic case and you add the inertia term to the mechanics, you are going to have real traveling wave speeds. Basically, the speed of sound in the material is going to be real, not imaginary. And if you think in terms of the numerics, you are going to have convergence as you refine, because otherwise you are going to have extremely localized deformations in regions with 0 thickness, and you wouldn't converge. So those are the benefits of polyconvexity in terms of mathematics, physics, and numerics. But there are extra benefits from the finite element point of view. And it is that it opens up for the possibility to come up with new alternative variational principles to the classical two-field that I presented here. So during my PhD, we went crazy with mixed formulations. And in addition to that two-field formulation, we ended up with, I don't know, 11-field formulation or something, where in addition to displacements and electric potential, the arguments of polyconvexity, F, H, J, etc., and their work conjugates were also part of the unknowns of the problem, and they needed to be discretized, satisfying an LBB condition that we didn't prove because it was impossible, but things seem to be working nicely. And you can imagine what the system of equations looks like for that mixed formulation, for that mixed principle. It looks like something like this. Okay, so it's extremely ugly, but things get easier when you do static condensation in the extra fields associated with the arguments of polyconvexity and the work conjugates. So just to summarize, benefits from the physical, mathematics, and numerics, and also the possibility of creating additional mixed variational principles. So how is time? 26. 26? Okay. So some simulations associated with this formulation, we explored not just those mixed formulations, but also high-order finite element formulations, and we explored the development of wrinkles. For that, I'm afraid that I need to go here. You can see what's going to happen due to the application of an electric field to that cylinder. Hopefully, the video is going to work, and it's actually working. It's working in the background, okay? It's in here. Application of electric field. 3 millions of degrees of freedom. I think we were using Q4 interpolation in here, and you can see that development of wrinkles in that case. I'm going to stick to this minimized version. Now, development of wrinkles on these. These wrinkles are actually really cool, I think. This is another video, but you can see here the wrinkles developing as a result of applying the electric field on the material. Okay, more wrinkles. You will see them. This was this one, sorry, and I anticipated to this one. You can also see wrinkles on a plate. This is the plate that I was mentioning before. You can see as we apply the electric potential, how these wrinkles are developing on this finite element simulation, okay? Which is something typical, which is going to occur in this material, okay?
What was on the left and on the right?
Sorry?
On the left and on the right of the video, the plots were different. What were we seeing?
Let me see. I think different boundary conditions.
Different boundary conditions.
I think so, yeah.
Both displacements.
Actually, I don't think it's different boundary conditions. I think it's different for more. Yeah, it is different boundary conditions. In one of them, I was applying Dirichlet boundary condition for the potential, and in the other one, I was applying Neumann, so electric charge, basically. And as a result, the patterns of the wrinkles were different. Okay. There you go. Now, I'm going to go relatively quickly on this part because it's the last part regarding basis of electromechanics. We've also tried to analyze the benefit of polyconvexity in the analysis of composites, of electroactive composites. And the first type of composite that we analyzed was a very simple one, was a rank 1 laminate composite. Essentially, you need to look at the macro scale, then you take a point, you make a zoom, and you will see the microstructure of this composite. You have like two materials, two faces, face A, face B, and you have this plane of lamination perpendicular to this vector n that appears here. You see that? And how do we do the homogenization? Every time you have a composite, you need to do a homogenization, right? In this particular case, we need to define relations between the deformation gradients and the electric displacement fields on each of the faces and related with the macroscopic F and the macroscopic D0. There are two conditions that need to be satisfied. This one, which is a simple average in terms of the C, which is basically the volume fraction between phase A and phase B, and this rank 1 and these jump conditions. Okay. Tangential jump in F is 0 and normal jump in D0 is 0. Okay. A condition or a definition of FA, FB, and etc. that satisfies these two conditions is actually this, where we have introduced this vector here and this vector here, which are equivalent. They are called amplitude detectors, and they are equivalent, if you are familiar with the field of homogenization, they are equivalent to the microfluctuations that you would see in the homogenization of an RB. Okay? And now, the way we define the homogenized energy, this would be the homogenized energy, is just like a weighted average of the energies of each phase. Okay? But you need to find the minimum of this with respect to alpha and beta. And that minimum yields two nonlinear equations, okay? From which, hopefully, you will get those amplitude vectors. The good news is that provided that the energies of those at the micro level are polyconvex, actually this problem has a unique solution. So at the micro level problem, that problem is very well defined. It's well defined indeed. Okay, that's the benefit that I wanted to see. We proved it. Now you can play with this, and then you can say, okay, I'm going to consider this type of energies for phase A and for phase B. Simple energies. Again, they are polyconvex. And they have the same shape. The particularity is that the mechanical properties of phase B are scaled through that contrast parameter, sorry. This is called mechanical contrast, and this is called electrical contrast. So basically, the mechanical and electrical properties are scaled, and now you can play with that scaling and also with the lamination orientation. And when you play with that, when you go for a real 3D application or simulation, you can see actually very fancy electrically induced deformations. Okay, we also incorporated viscosity on each phase. We incorporated a thermodynamically consistent model with viscosity, with internal variables, and so on. And we actually played with that, with the viscosity, with the relaxation times, and also with the orientation of the laminate in order to study the influence on the development of wrinkles on the material. Okay. And we also focused on a more complex microstructure like the one that you are seeing there, where you have an elastomeric matrix with a rigid inclusion. The way we modeled the matrix and the inclusion was through the same energy, but again, scaled through these mechanical and electrical contrasts parameters, all right? And typically, what do? You resort to the Hill-Mandel principle, periodic boundary conditions, and then you are going to get the microfluctuations. The conclusion here is that you can prove that provided that these energies are polyconvex, you will always get a solution for the microfluctuations. The bad news, though, is that in this composite and in the previous one, even though the microconstituents might be polyconvex And at the micro level, the problem might be well posed. At the macro level, the homogeneous response might not inherit the rank 1 convexity of the micro level. But then you can create polyconvex surrogates. Essentially, we did that exploring the concept of neural networks very recently. Actually, this has been just submitted. And what we do is, okay, we are going to create an energy using this sophisticated, more or less sophisticated neural network with hidden layers, etc., etc. And then what I want is actually to minimize the error between the derivatives of that energy that would give me Viola and electric field with respect to the possibly non-rank 1 complex data generated from this model. All right? But you need to be careful because we are going to request that this energy created through this neural network is going to be polyconvex. How? Well, requesting specific conditions on the activation functions and on the weights of the network. And we did that, and we are getting satisfactory results. Okay? This is a work that is expanding right now. Cool. This covers the first part of my presentation, and now I want to go to applications. Now that we have built all this, time please. 34. Now that we have built all this background, I met Jesus at Cartagena, like I said before. And as a result of that interaction, there has been a number of papers recently published on the application of topology optimization and optimal control problems for this specific type of materials. First application that I'm going to be talking about. In this application, I want to get specific shape morphing configurations for electroactive materials. And I'm going to try to achieve that through 3 mechanisms. And this is the first mechanism. In the first mechanism, you need to imagine this. This is going to be my actuator, which is upon which I'm going to try to impose that shape morphing configuration or that target configuration. How am I going to do that? Well, this is just an example. I'm going to decompose it in layers, all right? Top and bottom are passive. Passive means that they are just mechanical. They are not electromechanical. The dielectric elastomer is in between, is sandwiched, okay? I will impose electrodes in those two lines. I will create an electric field on that. And what I'm going to do is actually to design the passive layers, which are going to act like an exoskeleton or stiffeners. And I'm going to do that through topology optimization, in particular using the SIM method. Okay? How am I going to do that? Well, I'm going to decompose the regions between active and passive, like I said before, and I'm not going to touch the active energy of my material. That active energy of this material is not going to be touched because I'm not optimizing this. I'm going to be touching the passive or mechanical response of these 2 top and bottom layers. And the way I'm going to do it is like you usually would do it in the SIM method, proposing an interpolation of the energy in terms of a pseudo-density parameter that takes values between 0 and 1. And this is the way I do it. So this passive energy is interpolated like this, in terms of this rho, which is usually to the power of p, and p tends to be 3. All right? Just an add-on is that we did multi-resolution as well on this paper, which means that we don't consider a constant value of density per element. Actually, we subdivide in order to get a higher resolution of the density field in an element, which seems to be something easy, but it took us some time. Anyway, so how do you formulate this problem? This is just mathematical details, but the objective is what I wanted you to have clear. I want to get shape morphing configurations by designing the stiffeners. Typically, you need to minimize an objective function, which would be the distance between my deformed configuration to the target configuration. And then this is going to be constrained by PDE constraints. What PDE constraints? Well, the Ovarian equations I represented before, the 2 PDEs. And then constrained also to the energy interpolation scheme and to upper and lower bounds for the density field. How do we do this? Creating a Lagrangian and computing basically the sensitivity, because I'm going to be using a gradient algorithm. And my gradient algorithm needs this sensitivity, okay? And this sensitivity is the one that is going to allow me to update the value of the density field at each topology optimization iteration until I finally converge, hopefully. You get an example here. This example is motivated by the fact that actually we are not, this idea, this mechanism, it was not actually our idea. It was, like always, it was an idea from experimental researchers, all right? So guys from the research laboratory, they proposed to place stiffeners on the electric elastomers and get conical shapes, all right? And we took that idea in order to, using a different approach, not experiments, but inverse problems, see if we can get the same and later on more complex shapes, okay? And actually, we got similar results to what they were getting. This is something taken from the experimental paper, and this is what we are getting. We cannot match exactly the target configuration, but we are doing a nice job there. More complex shapes. There are like two, I call them mode 1, mode 2, basically. In this case, I'm trying to minimize the vertical displacement of this point and maximizing this one. And this one is a bit more complicated, minimizing, maximizing, minimizing. And as a result of that, you get this complex design. What is interesting is that for mode 1, you can play actually with the stiffness, the relative stiffness of the passive layer with respect to the electric elastomer. And when you play with that, you get these interesting results. You see that as you increase the stiffness, actually you get these very thin details of the passive layers. And also the same for mode 2. Okay, different concept, different application. Again, taken from the same guy's laboratory. The idea was taken from that. In this case, I'm going to try to get, again, shape morphing configurations, but throughout a different concept. And the concept is the following. I'm going to have layers of the electric elastomer. These layers are going to be sandwiched, or I'm going to intercalate electrodes, as you can see, with opposite polarity. And what I'm going to play with is not with the material. I'm going to play with the electrodes. I want to modify the electrodes. I don't want to have a constant surface. I want to design the electrode in order to generate a variable electric field which induces those complex shapes, okay? Essentially, if the red color here represents the electrode and the blue is no electrode, this is what you could see at each surface. These guys here are restricted to a surface. And the way I'm going to do it is through phase field, right? In order to represent the geometry of the electrode, I'm going to use a phase field. Phase field 1 means electrode. Phase field 2 means no electrode. In between, boundary. All right? Cool. How am I going to do it? By going crazy. Because, the way I'm going to do it is by trying to extending the effect of those phase field restricted in the surfaces. I'm going to extend its effect into the volume. How? By defining this minimization problem. These surface restricted phase fields are going to allow me to define this volume phase field, okay? By imposing that this new variable here is going to coincide, I'm going to apply Dirichlet boundary conditions in here, in here, in here, in here, in here. It needs to coincide with this. And then I'm going to apply a Laplacian here. That's it, okay? So I've extended into the volume the effect of the electrodes, and that effect is going to be incorporated into the energy. In what part? Typically, the energy is split into mechanical and electromechanical, right? Well, the effect of the volume phase field is going to be incorporated into the electromechanical energy, because the effect is very simple. If you don't have electrodes on top and bottom, okay, in the vertical direction, the phase field is going to be 0. If you don't have them. If you have them, it's going to be 1. Okay, so if it is 1, the volume phase field is going to be 1, which means that I'm not going to touch the electromechanical energy. But if I don't have electrodes on top and bottom, I'm going to be 0. So the effect is going like saying, you don't have electrodes, you are not electrically active. That's the trick, right? We did that, we formulated the problem like usually. You generate and you define your objective function. You're going to have PD constraints, etc., etc., etc. You can define this Lagrangian with these 2 PD constraints. And then you can compute the sensitivity. The difference is that I'm going to evolve the phase fields restricted in the volume through an Alenkant type evolution that you would see in phase transitions. With the difference, well, you will see the double well potential here, but the difference is now you have this guy here, which is modifying the evolution. This guy is actually the sensitivity of the Lagrangian that I presented before. When you do that, again, we need to justify the results with experiments. And this is the result coming from the experimental paper, and this is what we were getting in terms of the form configuration and in terms of shapes of the electrodes. These are the shapes of the electrodes. So essentially the electrode starts like this. Okay, we are getting something very close. For more complex shape morphing configurations, this is what we are getting, right? You want to, again, get this type of configuration, well, this is the design that you are going to need, and so on and so forth. In this one, actually, you can see how the phase field, sorry, I'm not sure why it's not working, because it was working before. There you go. Probably here. We are using phase field, and then you need to start with an initial guess for the electrodes. That initial guess has holes, and then you are seeing the electrodes evolving until you get a converged solution at the end of the video. Okay? And as a result of that design for each of the layers, you apply the electric field, you get this, which is your target. Time, please.
44.
44. Good. Okay. Has too many applications, so I'm going to present this one very briefly. You can achieve also shape morphing configurations by exploiting a different concept, which is don't touch the passive layer, don't touch the electrodes. Instead, on each dielectric elastomer layer, mix different number of dielectric elastomers. And that's what we are currently exploring. So basically, we are exploring the concept of multi-material topology optimization in order to get different target configurations, like the ones that you are seeing here. I'm not going to go into the details, but just for you to know that you can also use this concept in order to get complex shape morphing configurations and so on and so forth. The problem of magneto. The problem of magneto is a very interesting one. I'm going to remind it to you. Like I said before, we have two stages of activation. In the first stage, we design the magnetic residual magnetization. So you're going to put this material into the coils, and you're going to magnetize it until the point of saturation. And that saturation may change or may vary spatially. Okay? The key thing is how to design the orientation of the remnant magnetization. Because at the second stage, I'm going to put again the material, which has a remnant magnetization, within the coils, and this new applied magnetic field will try to align B0R with BA, leading to these complex deformation patterns. So the objective is actually to design B0R and also the value of BA in order to get a specific target configuration. All right? I'm going to be focusing on a specific type of materials where the permittivity of the inclusions that I put there is very similar to that of vacuum. And in that case, if you go to that paper, you see the way to model this is very simple. You can split the energy into two parts. Yeah, one purely mechanical, ideally polyconvex, and one which is magnetic. And the magnetic, you can see the form of it, is actually measuring the resistance of the material to align FB0R with BA. All right? The Ovarian equations are like in the case of just mechanics, with the change that Payola will depend on these extra terms. All right? And you can see the Payola that we get here, which is a non-symmetric term here. Okay? Like I said before, the idea is then to minimize the distance between my magnetically induced deformation to a target configuration subjected to the PD constraint that I presented here, and also to the fact that the magnetic polarization is a property of the material and its norm is a property. So I want the norm to be a specific value. And what else? And just that. And what I'm going to design is the orientation of B0R and the norm of BA. All right? So that's my problem. And as you can see, I'm going to be computing two sensitivities with respect to B0R and B0 and BA in order to, in an optimization process using a grading algorithm, to get a design for B0R and BA. All right. So this is the working principle that I explained before. So essentially, you have the material, B0R is this way, and then it's already magnetized, it's already saturized. You apply the magnetic field, and you see what's going to happen. The applied magnetic field is going to try to align both B0R with BA. Let's take advantage of that and of the application of inverse techniques. And then what you can get is actually configurations like this one. If you design properly the B0R, these are the vectors characterizing the orientation of B0R, or this one, or this one. All right? If you want more details regarding the theory behind this, please ask me later. It's a very, very fast summary of design in magneto-active materials. Last part, time please.
10 minutes.
10 minutes, okay. So we are not happy with the work that I have developed yet, so we want to go for every time more and more challenging problems, okay? And we said, okay, we are doing topology optimization into the field of nonlinear continuum electromechanics. Why don't we go into nonlinear continuum electromechanics and micromechanics, into the microscale, and see what happens? And that is the next part of the talk. So dielectric elastomers, I don't need to present you this like before, because I already presented these two pictures. What I wanted to tell you is that dielectric elastomers do not exhibit piezoelectricity. I'm going to explain this very plain, in a very informal way. So basically, you apply deformation, and a dielectric elastomer is impossible to generate electric field, all right? But if you go to the micro scale, to length scales which are small enough, if you apply gradients of deformations, essentially bending, torsion, etc., then you can get a net polarization, which means you can get electric field. Okay? So the idea was clear to us, and this phenomenon is called flexoelectricity. So the idea was clear to us, was let's apply what we know of inverse problems into the field of flexoelectricity with the aim of designing energy harvesters at the microscale. We have chosen a not very easy route in order to do that, because we have gone for what we call a micromorphic approach. Okay, the micromorphic approach is I'm going to explain it very quickly. So imagine the knot potato that I presented at the beginning, with the reference and spatial configurations. Okay, but on top of those reference and spatial configurations, on top of each particle, capital X and small x, there is going to be attached a microcontinuum. Okay, you need to imagine a microcontinuum there, and in the microcontinuum you are going to have these. Let me see, capital. I don't know what the name of this is, sigma, and this T. All right, which are actually, this is the spatial counterpart of this. So on top of the kinematic entities that I presented before in the macro case, now we have some kinematics in the micro level, and that kinematics introduce this microscopic deformation tensor G, which is not to be confused with F. And this G is actually relating both these coordinates that I presented before, between the spatial and the material. And this is a second order theory, which means that in addition to that G, to that microscopic deformation gradient tensor, I'm going to need its gradient, which is a third order tensor. So now that I've presented the kinematics, I want to present the Ovarian equations. The Ovarian equations are essentially the same. This is the same. This is the same. We have these two fields already presented before. But on top of that, we have now the new equations associated with the additional complexity that I presented. So in addition to the two kinematic fields at the microscale that I presented before, G and its gradient, you have its work conjugates. And this is the new PD. And the three PDs are coupled. The coupling comes through a constitutive law. Our strength in the paper that we just submitted was not in the proposal of the constitutive law. This is coming from a paper by Professor Steiner. He proposed this energy, all right? Where you can see some terms. This would be, for instance, a Money-Rivlin, mechanical, purely mechanical. This would be, for instance, an ideal dielectric elastomer. Why am I using ideal dielectric elastomers in topology optimization? Because it's topology optimization, and I want to do as simple as possible. okay, in topology optimization. And then we have this micromorphic term, which has the Frobenius norm of this third-order tensor, gradient of G, gradient of G. This is what they call in the paper a scale bridging term, which essentially is like a penalty term. The higher the value of kappa, the higher the link between the macroscopic and the microscopic deformation gradient tensors are. So basically, you would be enforcing that sort of, in a weak sense, F and G coincide. And then there is the last contribution, which is the responsible for the flexoelectric effect, and they present it in a specific form. And as you can see, that there is a link between the electric field and the gradient of the microscopic deformation gradient tensor. Okay, and now you can see the constitutive equations. In addition to the two ones that I presented before, you have two extra ones, and you can see the word conjugacy here. We went crazy in terms of, well, we didn't go crazy in terms of mixed variational principle. The way we formulated this was through a mixed formulation, because we explicitly didn't want to go, because I come from mixed variational principles like you saw before. I didn't want to implement C1 formulations, so I wanted to stick to C0. And but there is a downside to that. If you want to stick to C0, then okay, your fields are going to be displacements potential, and this extra microscopic field, and your system of equations is going to be larger. Okay, you need though to satisfy the LBE condition, and there is a numerical proof for this formulation in the small case, in the small string case, that tells you that you should go for this combination of finite element spaces. Okay, you do that. You embed it into the field of topology optimization. You are going to propose energy interpolations for each of the 5 terms in terms of a pseudo-density field, because we are using the same method in this specific case. The objective is actually to minimize an objective function. Okay? Typically, you would maximize the efficiency. Okay? In this case, I'm minimizing the inverse of the efficiency. Why? Because typically we minimize an objective function. All right? So I'm minimizing the inverse of the efficiency. And this is the inverse of efficiency. For this specific problem, if you take this objective function, you're screwed. Why? Because if you want to maximize electric fields, then you need to swallow hinges. The way to maximize localized effects is through the introduction of hinges. So it is good from the point of view of this objective function, but not from the structural point of view, this design, which means that basically you need to do a multi-objective function, a multi-objective topology optimization problem, where in addition to this, you add this objective function, which is basically kind of an envelope of the von Mises stress in the material. Okay? When you do that, you introduce this weighting parameter, and you can see what's going to happen. When this parameter is 0, you are left with the previous situation. And with the previous situation, we were getting, well, this is the way you would formulate it. It's essentially the same Lagrangian with PDE's constraints, etc., etc. The important bit here is the examples. Again, with W equals 0, we were getting this design. You increase W. This is actually a large increase in W. We are getting this. We don't get hinges. So how is the material going to generate flexoelectricity if it's not allowed to have hinges? Well, you need to generate gradients of strains, and a way to do that is through thickness variation and also through bending, which is what appears in the design. All right? Different example, this is compression, this is bending with a smaller beta. Smaller beta is going to induce that the topology between the case with omega 0 and omega 2 is going to be similar. Again, omega 0, you get hinges. You increase omega, you don't get hinges, but you get these, you see, those thickness variations and sort of curve elements in order to generate a sufficient flexoelectricity or a sufficient value of efficiency, inverse of efficiency. And just for completeness, we extended that to 3D, and we get similar results actually to what I was presenting this is a very similar case to the first case that I was presenting, which is this one. Okay, 3D, and if I'm going to give Ignacy the presentation, in case you are interested in the work that I presented before, there is a number of publications related to the previous part on nonlinear continuum mechanics, polyconvexity, etc. And then a number of publications on the application of topology optimization, optimal control, etc., to those problems. So if you want to check them, you are welcome. And the most important thing, I need to thank Fundación Seneca. I've forgotten it, but I need to say it, Fundación Seneca, for my Saavedra Fajardo Fellowship, which is the one that is giving me the job and the opportunity to present, to do this development. Thank you very much for your attention.
Thank you very much, Rogelio. This is impressive work and nice presentation. You fit perfectly the time. I think you have time maybe for one or two comments if anybody wants.
Only one or two.
Or more.
I have one.
Yeah, we have a-
So thanks for your presentation. I like it. You have given a lot of information in a short time, so I couldn't catch everything. Anyway, I wonder about the emphasis that you put on the fact of convexity or polyconvexity. So, in my experience, loss of polyconvexity is not the end of the world. So there is some different mechanics. The physics is the same. The mechanics can be different. The appearance of shocks, for instance, and another type of physics. So what makes the difference from your applications or your field you have deal with here? The fact that the material is not strictly polyconvex. So it breaks in some aspects, for instance, in the volume, in the volume strain, the chromatic strain, the polyconvexity. And then, of course, there are other type of physics that appears over, for instance, essentially in multi-scale problems, which is the field that I know better. But that is not something.
It's like you said, it's not the end of the world. From my point of view, if your material is no longer Rangone convex, you still need to do something.
Sure.
You still need to do something. You need to enhance your model with high order gradients. For instance, you need to regularize the problem, otherwise your boundary value problem is ill-posed. I've seen that in the context of mechanics in a dynamic problem. I was testing the Sambenan material and I said, why can't I use the Sambenan material? I'm not showing this here today. I have it in a different presentation. And then it was in the context of the twisting of a column. I've tried the twisting column with Javier many times in the context of fast dynamics. But I know that in the twisting of the column, in the bottom, there are going to be tractions and compressions. And the Sambenan suffers a lot in the compression. And it loses ellipticity in the compression region. And what we observed is actually, we verified numerically that there are regions where there are zero thickness strains, zero thickness areas. And you want to refine and see what happens with a different mesh, you don't get the same solution.
That's a very well-known problem in fracture, for instance. But this can be easily solved. It's not an inherent problem for mechanics or for numerical representation. It's just to use the correct numerical representation of that specific finite elements and so on. So apart from that, do you see any other kind of necessity of precluding or avoiding polyconvexity?
Avoiding convexity.
I mean, of requiring polyconvexity for dealing with these kinds of
well, if your model loses polyconvexity, if it loses Rangone convexity, it's because the model is wrong. Actually, it's not replicating a real material.
I don't agree with that. I don't agree with that. So you can have models representing some physics, which are not wrong just because the model is not convex. You have other problems. You lose uniqueness, you lose convexity, but that's something which is not, as I said, the end of the world. So for me, that is not a limit.
Well, I guess we wanted to at all costs, we wanted our system of PDEs to be well defined.
Okay, that's magician. That's pure magician.
Exactly. And we didn't want to include regularization terms depending on gradients, which could force us, like in the flexoelectric problem, to include an extra variable and then solve for extra degrees of freedom. So we decided to go for polyconvexity, which makes our life easier, certainly.
Any other question? Yeah.
Thank you for your very nice talk. So I have a question regarding these inverse problems for shape morphing. So your objective function for shape, is it on the shape or on the mapping? Right?
It depends. Sometimes it's the shape. I want a specific shape to be attained. And sometimes I'm just maximizing displacements or minimizing displacements.
But my question is you know, it's more, maybe it's a detail. It's about whether when you have a shape, I mean, you can achieve a shape with many different deformation maps, right?
Yes.
So the problem of finding a target shape is much more difficult than the problem of finding a target deformation map.
Okay.
Right, because in a deformation map, you know where every particle goes. If you just have a target shape, you don't know where every particle goes.
Yeah.
You just know that they have to fit in a given shape, right?
It's on the displacement field, actually.
Okay. Yeah, because
it's on the displacement field for many of the applications, for all the applications that are represented here, unless you use a different type of metric in order to measure distance between sets. You could use the Hausdorff metric, in which case now you don't need distance from point to point, which is something that we have explored in the context of optimal control. In that case, we were basically specifically focusing on shape, not the mapping from point to point. But in this case, everything is point to point. We could have used that metric there, actually.
Well, I mean, I don't think it makes a big difference in your applications, right? But so now, when you do this optimization and you have these linear structures, what happens if you have a mechanical instability during the process of shape morphing? I mean, do they appear? And,
yes,
and if so, how do you address that?
Before jumping into the multiphysics context, we jumped into just mechanics, and we actually tested very large deformations. I didn't have experience in topology optimization, and I thought it was going to be something straightforward, something easy with sim and level set. We have tested that, but you have plenty of instabilities, especially in the case of sim, instabilities associated with intermediate densities, and you don't know what's going to happen. So what we did is kind of an stabilization, actually, because those instabilities tend to be associated with fictitious structures, namely intermediate densities. The structure that you have at the beginning, you start with an intermediate density. Namely, you say, I want a volume fraction of 0.45. So I'm going to start with a pseudo density of 0.45 everywhere. But 0.45 is not your material. And then you're going to get instabilities associated with that evolution from intermediate densities to the final ones and zeros that you want. So what we did was to stabilize the elasticity density. We were adding the extra bit needed in order to make all the eigenvalues positive, until we get something that is similar to the final structure. Basically, we were trying to circumvent that process of instabilities at the beginning.
Okay, so the problem of designing structures that will be made as stable, that would be like mechanical switches, this would be very challenging.
It would be. Well, you can use tricks as well, because if you in those cases we were in mechanics, we were using force control. So we were applying force. But if you go for displacement control, things are a bit easier. All right, a bit easier. Still, you are going to have challenges, but in displacement control, things are a bit easier. In force control, if you want to rely on an arc length, you're going to go through serious nightmare. That was my initial state with topology optimization, and it was not pleasant.
Any other? Yeah.
Regarding to the last issue on topology optimization, so I think that you use two different methods. One is SIMP, and the other one looks to be like Jacob-Bernoulli equations or the level set method, right?
And phase field.
And why did you use both? So you commented that with SIMP you had some instabilities or some difficulties, which are well known, at least in the base. Yeah, there are so many SIMP methods that you don't know which one you are referring to when you talk about one of them. But in general, there is the classical inconvenience of that is that you have black and white solutions, and that are typically unstable because of the representation which is one element, one material that you simply. And this is not the fact in the level set method, in which you have, if you have a mesh as the level set crosses, the element has different materials at one side, not the other. So is that the reason for which you use both, or why did you switch from one to the other?
No. Well, in the mechanics, we use level set because we wanted to cover both simp and level set. And the instabilities were associated with the initial seed. It is true that you have ones and zeros, but you have an initial seed, okay, with holes. And that is not a real structure. And that the disappearance of the holes, the evolution of the seed was creating in the level set the instabilities until something similar to a structure was finally formed. Now, why are we using different approaches? There are several reasons. First reason is because I like testing things. Okay, I wanted to test phase field. I wanted to test sim. I wanted to test level set. I wanted to test everything. There are some of things that could be tested, like the topological derivative, but that's too challenging in this context. And there is another reason. For instance, depending on the problem, there are some problems for which I know that sim might not be adequate. Sim tends to give relatively good designs with ones and zeros if you want to maximize, for instance, compliance. That's a typical problem. All right. But if you want to get a specific target, not maximizing the displacement of a point, but no, I want the point to come to this specific location. In that case, sim might give you a range of densities which do not necessarily lie within 1 and 0. It would give you basically a composite material, and I've observed that with the phase field model, with the phase field method, especially in this problem of multi-material topology optimization here, I was not having this problem. I foresaw that I was going to have this problem if I had decided to use sim in this problem. So sometimes the problem is motivated by I want to explore, by let's say by willingness to explore new things, and sometimes it's motivated by, okay, I think there is going to be an issue here. Okay.
Thanks.
Question?
Yes, thanks for your presentation. Yes, so the same things we are saying here about the density. So I think we have like some kind of instabilities that we are bringing from the lower scale to the upper scale. So the sim method, we don't know how it brings these instabilities. So I am wondering if first thing is sim is losing a polycomplexity or not. And the other thing is this kind of regularization you are using just to stabilize the problem and not appearing these fictitious instabilities. Do you think if we propose something that is upscaling some physical microstructures that we average, then we can control these instabilities in the upper scale? And related with this, how we could do it, because I expect that it depends a lot on the length scale. It's backlinking, because backlinking depends on so how we can use microstructures to stabilize the problem and not appearing
Second part of your question, I don't know the answer, but first part of your question, which is, do we lose polyconvexity throughout the energy interpolation scheme? We don't. We don't, because the energy interpolation scheme is this one, all right? So essentially, you have a polyconvex material multiplied by this, okay? So this multiplying this is polyconvex, all right? And then we have, typically, this is the mechanics. This is what I do in mechanics. You have this, which is just depending on F, mechanics. And then you have this extra guy. This extra guy is basically a fictitious energy. It could be the same as this one, all right? But then you are going to have backlinks. Why do you want to have a moniribling to represent the energy of a void, which is going to give you nightmares and headaches? Instead, we use something which is linear elasticity multiplied by a really small parameter. For the void, we use linear elasticity. Okay, it's not going to be objective. I don't care, because it's the void. But still, this one is convex and this one is polyconvex, and this combination makes everything polyconvex.
Thank you. Okay. Let's end the session here. Let's thank the speaker again. See you all next week in the next session of the seminar course. Okay.